For example, you might choose previous 4 values. So at any point of time, if I am here and I want to make a forecast of what is the next possible value, what I'm going to do is I'm going to take the previous, this 1, 2, 3, 4, the previous 4 values, take the mean of that. The mean of these 4 numbers is going to be somewhere here. And I'm going to say that that is going to be the forecast of the next one. The actual value turned out to be here, but I made a forecast of that. Again, next forecast, I'm going to take the previous 4 values and make the forecast. This kind of forecasting method is called as moving average forecasting. Why moving? Because I'm moving the window over which I'm going to be forecasting. I'm going to keep the window length as fixed and keep forecasting 4 points at a time. Previous 4 points value, average of that is going to be my forecast of the next value. Why is that usually a good forecast? Because the values are stationary. The oscillations are going to be around some particular value. So average turns out to be a good forecast. If the values were not stationary, if the values were increasing, if I take the previous 4 values, I will be lower. I will be systematically under forecast. But when you have a stationary forecast, stationary data, moving average can give you an unbiased forecast. So moving average forecasting could turn out to be a reasonable forecast. So let's see the details of how you do this. I have a data set of number of products sold. Okay. And I'm going to use simple moving average forecasting. Different windows I'm going to use. The first forecasting I'm going to use is a moving average of window size 1. Over here is a moving average of window size 2. Over here, moving average of window size 3. Okay. Let's start with window size 3. For window size 3, if I need to forecast, I need at least 3 previous data points. So I can make my forecast only for the 4th data point, right? So I'm going to take the previous 3 values, 15, 20 and 16. Take the average of all of these 3 guys. Turns out to be 17. And that is going to be the forecast, my forecast for Windows 4. This is the next forecast. And each time I'm using the previous 3 values from here and making the forecast. In Excel, you would just write the formula here and drag it down. And you would have had the forecast of moving average of Windows size 3. This is moving average of Windows size 2. What would be a moving average of Windows size 1? Just the previous value. So the forecast here is just the previous value. Forecast here is just the previous value. Right? So I've computed the moving average window of length 1 forecast, moving average window of length 2 forecast, moving average window of length 3 forecast. What is the next column? I'm computing the error in my forecast. In this case, my error was 5, 4, 3, 5, so on and so forth. Right? These are all my absolute errors. And the average error turns out to be around 2.91. Okay. By taking just the previous month's sale as a forecast for current month, I'm making an error of 2.91. If I did a slightly better thing and did average of previous 2 months as the next month's forecast, my error turns out to be 2.68. Slightly better. If I take 3 months average, my error turns out to be 2.49, still better. Okay. There's no guarantee that moving average of window 5 is going to be better or window 6 is going to be better. What you need to do is, for the given problem, you try different moving average lengths. Find out which one minimizes the error. That is probably the appropriate window length. That's the right set of parameters for forecasting that particular data set. Okay. So the way you do moving average window forecasting is try different window lengths for the given data set. Find out whichever one minimizes the error. That's the right parameter. You're doing a parameter estimation. You did this kind of parameter estimation in linear regression too. In linear regression, you adjusted different values of slope and you found the best value of slope that minimized the error. So this process is no different than that. Over there, you search for the best slope and intercept. Over here, you are searching for the best window length that's going to minimize your error. Okay? Is the idea clear? What you're doing? Simple moving average forecast. So these are how the graphs look, how the actual data and each of the forecasts looks like. The only decision point is trying to find the best window which will give the least amount of error. Whole time series methodology requires that the window between two subsequent data points is fixed. So we do not remain outliers or anything in this process theoretically. What we do in real life is obviously slightly different, and we can talk about that later if you want. But this is the methodology. Is the methodology clear? Very simple. Take if for a window length 3, just take the previous 3 values and forecast that for the next month. That's your forecast. And the way you finalize on that window length is the one that minimizes your error for that given data, right? Absolutely. Right now we are not going to talk about that. We are going to figure out how to do forecasting when all average values all are available. In real life, of course, some data are missing. There are lots of imputing techniques that are there. So there is actually a impute TS package itself, imputing missing time series package itself that's available. But we are not going to be talking about that in this course. We are hoping that you know that missing data points can be forecasted through a variety of methods, and you choose whichever is appropriate for your business, right? But this is all given all the data. How do you do it? That's what we are talking about. Is the method clear? The next one is slightly we are going to increase the complexity of this. What we are going to do is again moving average, but we are going to do a weighted moving average. We are going to say that you are trying to forecast sales. The most recent month should be weighted higher than 5 months before that. 5 months before values should have less weight than the most recent month. That kind of averaging is called as a weighted moving average. The typical way weighted moving average, the weights are chosen are the following. If you choose a window length of 5, then most recent month will have weight of 5, previous month will have weight of 4, 3, 2 and 1, right? Those are the weights, and divide by 5 plus 4 plus 3 plus 2 plus 1. That's the way you compute the weighted moving average. And the same thing is shown here, how you computed weighted moving average for window size k equal to 1, window size k equal to 2 and window size k equal to 3. I will just talk about one of those windows, okay? But and I'll show you the formula as well. The files are attached, so you can look at the formula. So for weighted moving average of window 2, what I'm going to do is I'm going to look at the previous 2 months sales values. The previous 2 months sales values are 20 and 15. So I'm going to do, so I'm choosing window size 2, right? So 2 times 20 plus 1 times 15 divided by 2 plus 1. So divided by 3. That turns out to be 18.3. Okay. For window size 3, you would do 3 times 16 plus 2 times 20 plus 1 times 15 divided by 3 plus 2 plus 1. Okay. That's weighted moving average. And in this case, again, we see that as the window size increases for this data set, the errors are decreasing. What you would need to do is you would run R code asking you to search for different values of k, and the value of k that minimizes the error is the appropriate forecasting tool that needs to be used for that data set. Okay. Simple parameter search is what you're going to be doing in this. In the case of the revenue passenger miles, I could have used this simple moving average method and the weighted moving average method. I'm making this forecast. Okay. And what I find is for the mean absolute percentage error for simple moving average turns out to be about 4%. Whereas for the weighted moving average, you get a better value of about 2.73% error. So weighted moving average is a better method for forecasting if these two are the only ones that you're comparing. Is the idea clear? Simple moving average, weighted moving average. I don't want to disappoint you. I'm going to increase the complexity even more slightly. Right? This one is called exponential moving average. Okay. Now, what this does is something very similar to weighted moving average, but it's like you're extending the idea even more. In weighted moving average, we said that the most recent value has high weight, the next one lower weight, and beyond, say if you're doing weighted moving average of window 3, only the 3 windows have some weight, right? So you had 3, 2, 1, right? Exponential moving average takes the philosophy, why should we stop it with 3, 2, 1? Why not go beyond like 0.5, 0.3, 0.2, all the way to infinity? Let's use all the data, but farther and farther data will have progressively lower and lower weight. That is the idea behind exponential moving average. Okay. The way it's computed in practice is using this particular formula. So in exponential moving average, every single data point is involved in the weights. But as you go farther and farther, the weights get smaller and smaller. Then the weights are not integer anymore. The weights are all some real number. And the way the weights are computed, I'll give you the formula. But the way actual forecasts are done is through this following method. What you do is, you take the most recent forecast you have. You find out what is the error in your most recent forecast. You adjust your next forecast by the most recent forecast plus some fraction of the error you made. So each time you adjust your next value based on how much error you made in your previous estimate. That's what this exponential moving average is. Okay. This value of alpha is given by this particular formula. The window length, if you choose an exponential moving average of window size 4, then that's equivalent to choosing an alpha of 2 divided by 4 plus 1. So alpha value is 2 by 5. And what you're effectively doing is, every time you use the current value of forecast and adjust it by the error that you made in the current forecast. And your next forecast is determined therefore by how accurate your previous forecast was. So it's equivalent to constantly adjusting your forecast by the previous error that you made. This methodology is called as exponential smoothing. Okay. Philosophically, the method is not much different than the simple moving average. You're using past values and creating some weighted average. That's what you're doing. But formulaically, it appears different. And this interpretation is a nice way to think about it, because you are effectively saying, if you remember the sales data, when I said the next month's forecast for sales, when I use k equal to 1 window length 1, I said next month's sales forecast is same as this month's value. If I do that forecast, the error wasn't all that terrible, right? So if I next month's forecast, I use this month as the forecast, the error is not all that terrible. But let's say I find out exactly what that error is and adjust for it. Hopefully I should get a better forecast. That's what this methodology is doing. Okay, it's adjusting each time by that error. This is called exponential forecast, and I'm giving you here the formula that is done, that is used in each case to update the windows. Okay, I'm giving you the Excel sheet too, so you should be able to look at the Excel sheet and see how it is done. The command for doing this in R is simple. Simple moving average command is SMA. Weighted moving average command is WMA. Exponential moving average command is EMA. Right? And all you need to do is specify the window length, and it will do these computations accordingly. But you should look at the Excel sheet to make sure that you understand how it's actually done. Okay. In this particular example, it again turns out as you increase the window length, your error is getting smaller and smaller. And the best value of window to choose in this case also, you need to try out different window lengths and find out which one minimizes the error. And that's the appropriate value of parameter for that particular data. Okay. In all of these data sets, you're doing some fitting. Whether it's linear regression, logistic regression, or any of these methods, you're doing some fitting. You're trying to find the appropriate parameter for that data set. In this case, it's one parameter that you're fitting. Yeah. That is not the linkage. The number of data points, what matters is the patterns in the data is going to determine what is the appropriate window length to be used. What you will see, for example, is when you have a sinusoidal series. Okay, when you use too small a window length compared to the so here is my sinusoidal series. Okay, big sinusoidal wave, right? If I use a window length the window length of this, right? I'll be averaging here and making the forecast of all of these points as the average of these points, which will turn out to be somewhere here. Average of all these points will turn out to be here. That's a very poor forecast for this, right? However, if I use the entire window as a window size, then average of all of these points will turn out to be somewhere here. That might turn out to be a better forecast. So the patterns in the data will determine what is the appropriate parameters that's going to work for you. We are not talking about seasonality at all in this. We are just looking at simple moving average. That's all we are doing. In this case, it's exponential moving average, but it's conceptually similar. But I want you to remember this one interpretation of this method. Exponential moving average uses the error that we made to keep updating its forecast. And that seems intellectually appealing, that to make forecast, if you identify how much error I'm making and adjust that error, account for that error, then your next forecast probably is going to be better. That to me is intellectually appealing. And we will come back to that particular idea before the end of the class as we increase the complexity in the model. Okay. How do you feel about what we have talked about till now? So at this point, there is no levels at all. This is telling you what this number. So can someone interpret this number for me? What is this number telling me? 2.35. What is it telling me? No. So what you are doing is, I am making forecast for every single point, right? Yeah. How many data, how many sales, what is the likely sale next month is what I'm forecasting. What this error is telling me is the amount by which I might be off on average. margin of error, in this case, about 2.35 will be the size that is going to be, I'm off by. So if the average order is around 15, I might be from anywhere between 13 to 17. That's what this error number is telling you. So the size of this number can be interpreted, can be connected directly to this real order, but it's not bounded like R squared or anything. R squared was nice and bounded between 0 and 1. So this one is not bounded, but it also is giving you some information. Correct. It's absolute error and then average. So this is mean absolute error. Yeah. So there are multiple error metrics. So when you say standard deviation, there is what you are actually talking about is root mean square error. That's what you mean, and that's a good metric as well. The business user defines some metric. He will tell you, this is the number I'm trying to minimize. We all like root mean square error because it's got the nice connection to standard deviation. So we like that error. But most business users find this number more intuitive because it directly is telling you on average how much error I'm making. So business users like this. But again, so you as a data scientist, once you know which metric I need to minimize, you will vary the parameter, find out the value of metric for each of the parameters. So whichever one gets you the minimum one, that's the right parameter which is used for that particular data set. Absolutely. What's happening is this. Any of these spikes in the data is getting averaged out. You are doing a moving average. When you average out, you're losing information, right? So you are smoothing out all of these spikes. So as window length increases, the curve gets progressively smoother and smoother, right? So the error values, depending on the data set, the error values might increase because of that, or error values might decrease because of that. We don't know. It depends on that particular data set, which is why this experiment needs to be done. You run a loop and find out for the given data set which is the best value of moving average that minimizes your error, and that's the one that you're going to use for future forecast. Any other? So for the data set of revenue passenger miles, previously I showed you the errors for simple moving average, exponential weighted moving average, and exponential moving average. Turns out exponential moving average method performs better for that data set. But then that's not always a given. You need to check all of these methods, find out whichever method does best, and that's the method you're going to use for future forecasting into the future. How are you feeling about this methods that we have talked about? Okay. These are, in terms of level of difficulty, if you rate these methods as 3 on a scale of 10, the next set of methods is going to be like 7, and before you reach 20, right, on the final. So let's. What I'm going to do is before we take a break, I'm going to give an introduction to the next set of methods that we are doing. The next set of method that we are doing uses this idea of moving averages. Okay, particularly the exponential moving average. Exponential moving average had this nice feature of using the forecast error that we made in our most recent forecast to update, to try and give a better forecast for next window. That feature looked very attractive. The next set of method uses exponential moving average as its base.